Welcome. This Tech Talk was recorded live at the 2023 International Microwave Symposium Microapp Theater in San Diego. This Tech Talk presents the conditions necessary for the multipaction failure mechanism to occur. Once these conditions are understood, measures can be taken to mitigate this unique problem on spacecraft applications. Enjoy the presentation.
My name is Sean Moore. I'm the CTO of Quantic TRM. And I'm going to talk about multipaction today. But I think the thing to realize about multipaction, before we talk about how to mitigate it, the first thing we have to understand is what is multipaction. Because you can't solve a problem unless you know what you're trying to solve. So really, what multipaction is a direct electron transfer event that happens between two nodes of the circuit. It is a resident event, and it is a cascading event where more electrons are released after each impact. How is this different from other sort of breakdown events? Most notably, the one most people are most familiar with is corona breakdown. So corona breakdown is an event where you have a cascading event of an ionization of a medium or a gas between two electrodes. Multipaction is a resident event. So it's by nature, it is a different failure mode. And as a result, the mitigation for that can be different. And a thing to realize is that with multipactor, since it is a resident event, there are actually individual things that need to be consistent to have this event actually happen. So the first thing you need to have, basically there are four things that you need to have a multipactor event. The first of these conditions is that you need to have a free path for the electron to pass between the electrodes, that nothing is in the way. So therefore, we need to have a vacuum in that area to actually have this event actually happen. So what we need to have is a nice clear path from one electrode to the other in order to have this full path. The second condition that we need to have enough electrons available on the receiver to emit more electrons so that it becomes an avalanching event. This is not just a single event with an electron bouncing back and forth. This is as one electron bounces, it then releases more, so the next path is more, and then more, and then more. It continues to build. So what happens here is that in order for a surface to generate enough electrons, it has to be, in general, something that can conduct the field, and it has to have enough potential voltage on it to be able to have enough electrons so that it can be released. The third condition is one that, quite frankly, is quite fascinating. The third condition is that it needs to be a resonant event. Now, it turns out that electrons, since they have mass, do not move at the speed of light. They move relative to the electric field that is imposed on them to generate how fast they're actually moving. So there is a dependency on the voltage of the field versus how fast the electrons are moving. So you can see in the graphic here, as far as to sort of a voltage versus electron acceleration. We're working on the very, very low end of the curve here typically, but it shows the fact that this is a nonlinear event. So what has to happen now for this event to happen is that for the time it takes for the electron to cross the gap, the electric field needs to reverse itself so that when the electron hits the secondary element, its field is now reversed, and then it's going to release more electrons back to the primary. So it becomes a resonant event. So right now, to summarize, we have a vacuum. We have to have a clear path. We have to have a resonant event, and the surface has to be able to release more electrons than hit it. And the fourth condition is that something has to be a catalyst to start the event to happen. So in this case over here, if we're on a spacecraft, there are lots of electrons and radiation flying around that have that initial impact on the surface to begin this whole resonant condition to happen. So in free space, on a spacecraft, these particles are everywhere. When we do multipaction testing here on Earth, we have to put a radioactive source in there to be able to kick this whole process off. So the reason why we worry so much about multipacting when we're on a spacecraft is because on a spacecraft, by nature, 2 of the 4 conditions are automatically met. We have a vacuum, and we have availability of free electrons. The frequency, gap, voltage are interdependent on each other, and there are certain combinations of this that will cause a multi-factor event to actually happen. So what happened as we start to go through and configure these various configurations, we then go through and define multi-factor regions where multifaction can happen if this gap size, frequency, and voltage are all happen simultaneously. This is typically shown on the Hatch-Williams curve that's on the screen right now. Each one of those rectangles that are sort of going up on a diagonal will go ahead and define a region where this resonant condition can happen for each mode of the energy that is within that gap. There are multiple rectangles on the graph you see in front of you. What each one of these rectangles represent are a mode for the field. You think about this a little bit almost like a waveguide mode as far as to how the various fields are built up, and therefore there are a series of rectangles, each one corresponding to one of those modes. What we end up with, since these rectangles and these modes are essentially overlapping within this graph, we end up with this very large region where multipacting can occur. So what we want to do is we want to make sure that as we're designing components, that none of our voltage fields, our gap sizes, and our frequencies, when we go through this voltage versus frequency times gap size, ends up in one of those multipacting regions. So this is very important to make sure that we stay out of those regions. So how do we do that? We do that by going through and making sure that that the gap sizes versus frequency does not fall into those regions. So we do that by having interlocking dielectrics. We try to go through and make sure that we actually eliminate gaps. As part of our design process, we go in and we go into structures such as strip line more so than microstrip. If we have to go into microstrip, we have to make sure that we make sure these gaps and frequency that we're working at do not violate these areas. Some of the questions that happen to come up here as far as to whether with multipacting in general does multipacting have to happen between 2 conductors? The answer is no. It can happen in a wide variety of other sorts of applications. What's important though is that as the electron moves across the surface or through a gap, if a field reverses and then pulls it back onto that same surface, you can have a multipacting event with a single surface. It does not necessarily have to be between 2 conductors. It does not necessarily have to be between a conductor and a ground plane. It can happen in a wide variety of events. If electrons are released, go out, are pushed away by an electric field, and then pulled back in, whether it is between 2 plates or within one surface, it can still happen. So we have to be very careful about exposing any kind of conductor where there is a significant electric field that can cause this sort of resonant condition to happen. Believe it or not, multipaction can also happen on the surfaces of dielectrics if there's enough free electrons available. So the way that we work this here, like I said, is we try to control the absolute the variables that we can control. We cannot control the frequency that we're operating at. That's part of the system requirements. We cannot control the voltage. Those are usually things that are things that are given by our parameters that we are looking at. The vacuum is certainly something that if you're on a spacecraft, especially in a passive microwave device like the parts that Quantity TRM builds, you're going to have a vacuum on the parts. And the fact that the component is on a spacecraft, well, that's what it's supposed to be doing. So what we have to do is we have to go in there, and like I mentioned before, we have to make sure that we watch these gap ratios to make sure we stay out of the multi-factor region. One key element there is to go in there and by filling these voids area where we have conductors that are beginning to get closer together with some sort of dielectric to eliminate these gaps as we're going through the whole process. So basically, as a short summary, multipaction is a direct electron resonant event. The fact that it is resonant is key. There are many things that make things resonant. We have to make sure that the voltage reversal happens at a time at the same rate as the electron is moving across the field. And in order to be able to, by changing any one of those parameters, we can break the resonance condition and therefore prevent multipaction from happening. I want to say also that the effect of what is the effect of multipaction to an overall system versus a corona breakdown event. Initially, when multipaction happens, what happens is the noise floor begins to increase because basically we're getting noise from the electrons bouncing off the surface. This sort of a increase in the noise floor can initially cause you to raise the noise floor, decrease your signal to noise ratio, and then ultimately have you lose your signal once the noise gets high enough so that you lose your signal. In extreme cases, that it can actually damage the circuit in the very same way that a corona breakdown can damage the circuit if the voltages are high enough to actually cause that damage. What's fascinating, though, about the multi-factor event is that the power levels and voltages that are required to have this resonant electron event happen are extremely low. And I think that is the key as to why most people tend to overlook this event unless you've been burned by it in the past. So it is one of those things that it can happen at very low voltages and very low power levels. In general, this can happen at like 20 volts. I mean, it doesn't take much to actually have this fail. This is not a 1,000-volt sort of failure mode. It is something that can happen at a very low voltage, and it's something that really takes a lot of good consideration to make sure that you avoid that sort of a multi-factor event. So that's all I have for today. Well, thank you very much for coming. And if you wish to discuss more about this, I'll be in the back a little bit, or I'm at booth 1947. Thank you.
Thank you for watching. Quantic TRM designs and builds world-class passive microwave components. We differentiate ourselves by working with our customers to jointly solve the unique engineering challenges that occur when designing state-of-the-art performance systems for unique environments, such as spacecraft and military applications. At Quantic TRM, we don't use a one-size-fits-all approach. Each problem is unique, and the solution to that problem needs to be tailored so the best performance can be achieved. As always, we would love to hear from you and are looking forward to working with you on your next project. You can contact us through our website, www.quantictrm.com, or through the engineering hotline. The number's on the screen. Thank you once again, and I'll be seeing you on the next Tech Talk very soon.